Do you have it?
Yes.
Good.
I have
Good.
this.
Good morning, Sam.
Oh, thank you. Does anyone else have a test so I actually put it into a folder and didn't lose it? Because here's a test right here. A sad, lonely test that's not in the right place.
Are you sure you want me to start the movie yet? Just
Alright,
asking.
go ahead and start.
It's been running.
Hi, Sam. Alright, so electrostatics. What is electrostatics the study of?
Charges at rest.
Charges
Yes.
at rest. Now, from chemistry last year, what is an ion?
It has a negative or positive charge.
A charged
Straight
particle?
electron.
Weren't you
Yeah,
just
they can be
talking about
negative
that
or positive.
outside?
Probably.
Yeah, I'm pretty sure I heard you say that.
Yep. So an atom or a group of atoms that has gained or lost one or more electrons. So a charged particle. And what do we know about like charges?
They repel each other.
And opposite charges?
Attract.
Attract. And the strength of the attraction depends on a couple of things. What might the strength of the attraction depend on? Let's say I've got a negatively charged particle and a positively charged particle.
The strength of the charges.
Yeah.
Strength of the charges and
The distance between them.
the distance between them. Okay, and you can see that in the equation that we'll use later. So some substances are naturally conductors and some substances are naturally insulators, and when we make our electroscope we'll use that to our favor because we'll use a conductor as the little filament in the electroscope, and we'll use an insulator to hold on to it so that the charges that we are using can't escape somewhere that we don't want them to go. So a conductor, charge flows easily through a conductor. Most metals are good conductors. An insulator, charges don't flow very well. Most nonmetals are insulators. What is the law of charge conservation? Just like every other law.
All of the electric charge in the universe stays like it doesn't get more or less.
It's
It's
constant,
like the
yes.
energy or whatever.
Yes, net charge in the universe is constant. So when we play with our electroscope today, we're going to charge it two different ways. We can charge an electroscope by induction, we can charge it by conduction. So conduction just basically means that you're going to touch the electroscope with something. Induction means that the charged thing isn't going to be touching the electroscope, but something else might be. So if the actual charged thing has contact with the electroscope, that's conduction. And if it doesn't, it's induction. And I'll talk about how each way that you can charges at a certain, well, like if you charge by induction, you're going to impart the same charge as the charged thing that you're touching your electroscope with. If you charge by induction, you're going to impart the opposite charge as your charged object. So you can control if the electroscope is positively charged or negatively charged. If you have a negatively charged balloon and you charge your electroscope by conduction, you're going to impart a negative charge to the electroscope. If you use a negatively charged balloon and charge it by induction, you will impart a positive charge to your electroscope, which is kind of interesting. So when you're charging your electroscope, I have the loudest chair ever. When you're charging your electroscope, what moves in an electric current?
The little
Electron.
Electrons. Can protons move in an electric current?
No.
No. Protons are stuck in the nucleus of their atom. They don't move. So when you impart a positive charge to something, what are you doing?
Taking away electrons.
You're taking away electrons. You're not adding protons. So I had somebody answer a test question like that. I added protons. No, the protons don't move. Just electrons flow. More electrons can gather in one place and give a negative charge, or electrons can get away and give a positive charge, but the protons don't move. It's just saying.
If you do find yourself adding protons, I think you're like making nuclear reactions or something.
Yeah. Well, protons just don't flow, so yeah, if you're adding
you just have
protons.
like a proton floating around in the air.
Well, when you have an acid, you
That's
have loose
wait.
protons, basically, because the hydrogen
They would be
nucleus
moving that.
is.
That's your hydrogen ion. When the electron leaves, you just have the. Isn't it just like one
Yeah.
proton left?
Yep.
Wait, do they have a-
Unless it has some neutrons. Some hydrogen nuclei have one or
yeah.
two neutrons, but
I remember
Um,
that from chemistry. I thought it was funny.
yeah, but you just have a bare proton floating around in solution with an acid. But you don't necessarily have a net positive charge because you also have whatever the hydrogen was donated from, which now is a negative charge, so you have a net neutral charge in there. And just to review, because I actually think the test asked you something like this, an electron carries what charge?
Positive.
Negative. And a neutron carries what charge?
Nothing.
Neutral. And a proton carries what charge?
Positive.
Positive. A proton is in the nucleus, positive charge. Electron outside the nucleus, negative charge. And it doesn't orbit like a planet, it zips everywhere. And it jumps from orbit to orbit, but it's not allowed to be between orbits, so we don't know how that happens, which I love. So, we've got math, we'll do the math here in a minute. Drawing these little diagrams. Did you all read the part of the chapter where you have to draw the lines?
Do we have
No.
to draw them?
No, you didn't read that. Yeah, I don't remember. Electric field lines, did you read that yet? That's next week. Okay, so we won't draw any electric field lines today. Alright, so let's do review questions just so I know where I'm supposed to stop talking today. And that way, what review question did you stop on?
5.
5. I need to draw lines on every paper so I know where to stop. I don't have to ask every year. Okay, well, we just talked about number 1. The 3 particles that make up an atom, the proton, which is positive, the neutron, which is neutral, the electron, which is negative. And so he just wants the signs, that's fine. Number 2 says matter is made up of atoms and therefore has positive and negative charges. Nevertheless, most matter has no net charge. Why?
Most have an equal number of positive and negative electrical charges.
Right. Okay, so most atoms, if you have just a normal, like off the periodic table atom, you have an atom, say carbon, which has 12 protons in the nucleus, will also have 12 electrons, so it'll have a balanced amount of positive and negative charges. Number 3, compare and contrast charging by induction and conduction. Right.
Conduction is direct contact, and induction is like kind of like through the air.
Yeah, and you'll actually see this really well with the electroscope. When you charge by induction, the charged object won't touch the electroscope, but you will be touching the electroscope.
Would that be like? Would that kind of be like with lightning?
Tell me how.
Because you know how like you have the charges from like the clouds meeting the highest object.
Yeah,
Like
with
if there's a
potential
person-
difference.
So would that be induction or? Because I was just wondering.
Well, that would be an electric potential. Did you guys learn about that this week?
No,
No.
Yeah, the two clouds, like having 2 different charges separated by a distance is an electric potential, and we will learn about that, but apparently not this week. Soon, I think. Maybe next module, because that sounds like something we'll learn about with a capacitor. But definitely we're going to go there. Number 4, you have a negatively charged object and you want to give another object a negative charge. Should you use induction or conduction?
Both.
One. Pick one.
Conduction.
If you want to give it the same charge as the object that you're using to charge it, you should use conduction. And the electroscope lab will clear up any questions you have about that. What is the difference between an insulator and a conductor?
The insulator doesn't have electricity in it, or doesn't let electricity go through it, and the conductor does.
Okay, and metals generally are,
Conductors.
and non-metals obviously not generally conductors. Okay, now math. the math in this module, I don't know, how many practice problems did you do?
6.
So you've already revisited your fun cosine and sine business.
Yes.
Okay. So, and you did the hard problem. Alright, so we're gonna spend a good bit of time on math and do the electroscope lab, leaving us practically nothing to do next week probably, but, that happens. Purple pen. Alright. So, we start out with some easy stuff. Now this equation should look, and I'll put it here where it will be one of those equations you should memorize. Is that right? Is R squared? Yeah.
Yes.
So what does this look like when you look at this equation? What other equation that we've used in the past does it look like?
The gravity equation.
It looks like the gravity equation. Now, do we know why the electrostatic equation would look like the gravity equation?
You said God must like symmetry.
Maybe. Maybe, or maybe there's something we haven't discovered yet that really links them. I actually cut the script in today. So, anyhow, it should be very familiar. F obviously is the force, the electrostatic force. K is a constant, which is given at the top of your test and at the top of the practice problem paper, which is good. Q1 is the charge of one of the charged objects. Q2 is the charge of the other one, and the radius squared, obviously the distance between them. Also, when you're talking about the orbit of an electron, he's going to have you use this equation. So when you set these two equal to each other, what do you get? Let's see. Well, anyhow, if you have an electron orbiting, then your electrostatic force is equal to also an orbiting kind of force, right? So you can use this. Right? You can use that, you can cancel out
R.
an R, and you can find an unknown that way. And you will have a problem like that on your test, and there's probably one like that here in about 2 seconds, right? Possibly.
If
Or maybe
there's
next
something
week.
wrong.
Next week, yes, number 10, practice problem, we'll use that, so
Okay.
just so you're ready for it. But I'll leave that on the list of good to know equations for this week. So, number 1 says 2 charged particles, Q1 has a charge of 6.7 coulombs, Q2 has a charge of negative 3.1 coulombs, or 1.2 meters apart. What is the instantaneous electrostatic force between them? And just to stop and ask, why can we only calculate an instantaneous electrostatic force?
Is there gonna be moving?
Why are they constantly moving?
Because of the force that's here.
Okay, so they
Or
don't ever
repel.
hold still. If there's an attractive or repulsive force, they're moving, right? So you can only lock them down for one instant at this distance and this charge, and then they're gonna continue to move. So you can
So-
never figure out a constant electrostatic force because electrons or charged particles are always gonna be moving.
I guess would there be like an acceleration unit for it? Like you could take a bunch of instantaneous rates and figure out
Yes,
how fast their
that would be
speed-
calculus-based physics. Come back next year. Go to
Okay.
college for that.
Well, I
don't wanna
mean,
do
it
that
wouldn't
math.
be hard. All you have to do
Yes.
is do a bunch of these and
And
then
graph it.
divide
There's
that
really
out.
an equation that makes that way easier.
Okay.
So you don't have to necessarily graph it every time. There's an actual equation that helps you out. But for us, we're going to do it this way. So what would we get for the force if we plug in K, Q1, Q2, and R?
1.3 times 10 to the 11th newtons toward each other.
And note that he has a vector there, which is important because that is a vector. You need a direction.
Was it negative? It happened on negative 1.
Well, that's what the negative means.
Oh, okay.
Because it's
Because-
positive and negative, so they attract each other.
Right, you have to like look at what you have and decide, okay, if one's positive and one's negative, they're attracted, so they're gonna move toward each other.
So
And
in
you don't
tests,
put the
Do you want
signs.
to put the negative sign?
Not
Or
in
does
the
it not really
equation.
matter if we have the?
You don't have to put it in the equation, but you do have to have a vector discussion of direction. If it helps you, that's fine. And I think, don't they normally do, negative to the left and positive to the right?
Well, doesn't it depend on?
Or is that just me?
Well, I mean,
Is there a standard?
if you move a little bit, then it's not on the left anymore. Like if you go around the other
I
side
think
of
it's
it.
the way
So
how they're like placed together. Like
Okay.
if you have like these,
Mhm. Well, we have to talk about direction a lot here. Maybe
so I'm just
thinking of
writing
something
like
else.
towards each other or away from each other. So I
Okay.
think that would work.
Maybe next
But
week
that's-
we'll have a slightly bigger discussion. And in problem number 6, we're gonna have a massive discussion. And then I'm gonna tell you that if you do not do extra practice problem number 6, sad things will happen on the test. Even though I'm going to, as much as I possibly can, tell you the answer today.
why is there a question on the test like?
Yes, extra practice problem number 6 has, it took me, even after I looked at the answer book, I didn't understand it the first time I did the problem. I was like, I don't know how to get the angle, I don't see how this is even right. My husband had to explain it to me. So, I have a big warning note on here that I'm going to explain why extra practice problem number 6 is unusual. Because it did not jump out at me, and maybe you guys could see it immediately, but I didn't.
What is the problem with it?
We'll go there here in a minute. Let's get there first, though. Number 2 says 2 charges. Q1 is 0.32 microcoulombs. Q2 is 0.55 microcoulombs. Exert a mutual repulsive force of 2.5 times 10 to the 5th newtons. How far apart are they? So, what are you going to solve for?
The radius.
Solve for the radius. And you plug and chug, and you get what for the radius?
0.080 meters.
Yes, 2 significant figures because you have 2 in the constant. Did anyone not get 0.080 meters? Good. Number 3, 2 particles of equal and unknown charge are 45 centimeters apart. If their electrostatic repulsion is 2.2 times 10 to the 5th newtons, what is the magnitude of their charges? So what will I do to this equation to figure that out? If they're equal charge, then I can say force equals K times Q squared divided by R squared, right? Because if they're equal, they're just going to be multiplied by each other. So then I plug in 2.2 times 10 to the 5th newtons and K, nasty little
Newton meter squared per coulomb squared.
times Q squared over my radius, which is 0.45 meters squared. Alright, so what do I get for Q if I do this times that divided by that to the square root of, I get what?
3.3 millicoulombs.
Micro? Is it
Micro.
milli?
No, I think it was milli, because there's 10 to the negative third.
Oh,
I think.
I
could
always
be
said
wrong.
micro, you might be right there. Alright, so that isn't what I got. Did anyone else get something different?
I think
Yeah.
I completely messed up the problem.
Oh,
I'm not saying I didn't either, but that's
2.2.
you got 2.2? I got 2.2.
That's
I
what
got
I
2
got.
points.
Alright, let's
Okay.
all plug in and see what we get. 2.2 times 10 to the 5th times 0.45 times 0.45 divided by Q by square root of.
It's just,
Yeah.
I just got 1.1. I think
Oh,
I'm doing
no.
something wrong. Oh yeah. Okay. So hang on. Yeah, this is what I got before. I think I did something wrong.
Plug them in, I want to see answers on everyone's calculator.
Maybe I can pull it up.
Oh, you already had it.
I don't know how much.
You have it right on your paper, so obviously you got the right answers. Is this for me?
It just requires a lot of little parentheses.
Well, cause I
Hi
changed
Sam,
them
sorry
to,
I
like-
just walked right in front of me. How's it
Mine is
going? Oh, your calculator? Yes, absolutely. My calculator is very friendly for this kind of math.
So this is how it's supposed to look, right?
2.2 times 10 to the 5th. Oh, 0.45 squared.
Oh yeah, that might be my problem. Oh yeah, that was a problem. Okay, that's 2.2.
Yeah, when I cancel out the meters squared, I'm not canceling the square for the 0.45 there. Hit EE and then hit a 5.
This is nice.
Yes.
When we're converting from millicoulombs to just, or no, coulombs to millicoulombs, you just take it and say times 10 to the negative 0.
Yes.
I thought it was. I converted them. I don't even know. Well, I got 2.2 now, but I was in one. I got like 2.3 times 10 to the 2. Cause I converted.
Oh.
Cause I converted them to. Cause I thought they were milla, and I changed them just to. I divide them by 1,000.
Oh.
So that's what I did the first time. But I got 2.2 just now.
Times 10 to the negative 3.
Yeah.
Okay, good.
You wanna try this one?
Yeah, I did it.
Sam is being entertained by the clicking of calculator buttons. Wow, he's got it times like a bunch of something.
Oh.
You must have an order of operations problem. It's dividing the 0.45 squared by the 9 without dividing the 2.2 times 10 to the 5th by the 9.
What was it?
Hey, how do you do the
You need,
next
like,
thing I wanna see?
More parentheses even, or you might need to do it
And
2
get
steps
the
or
double,
something.
you can eat and then you press whatever.
Alright.
it is.
Just
And you just
times. Parentheses.
whatever.
Anyone who has done all of this can start blowing up a balloon probably.
I'll do it.
Oh, how do you do it? How do you do this?
Yes, everyone gets a balloon
Oh,
that wants a balloon.
Just, hit answer. Answer.
But if you've been coughing and sneezing, don't share balloons.
Yes. Keep your own balloon to yourself, please. And if a balloon should break, don't leave any pieces on there.
I'll blow it up.
Obviously.
Don't you have to like stretch your balloon before you blow it?
No.
I did that. This.
So keep them
But that's not
occupied.
I would put the 9 in.
Yeah. Well, you.
I don't see.
Put
That
9.0.
was.
Put 9.0.
There's a time part I always found.
No.
Are we supposed to tie it?
No, you click second.
Yeah, and then take the square root of that.
I need to W.
Mr. Matthias,
Yes.
are we supposed to tie it?
off. We're just using it to hold an electron.
Oh, this was how.
Rub it in all our hair.
Yes. If anyone uses a lot of product, then you're gonna rub it on your friend's head or something.
And if you haven't washed your hair in several days, then also don't try it.
Right. Just say you use a lot of product
I think I
to
got
save
it
yourself the
right.
embarrassment. And
Is that what you got?
There.
I didn't condition today, so I'm like ridiculously puffy.
Oh. Thank you.
Oh, here's your.
So here, maybe if you suspend your balloon from a string.
Look at that.
Did you guys get it? They have got it.
Got that.
I need scissors.
The laser
Does anyone
shines
have a
through
Sharpie?
balloon.
I.
Oh, my balloon.
Eh.
Your
You
balloon's
can
too
write in
small.
dry
Make
erase.
it big.
If it's too big, I can't hold it with my hand though. I have to be able to.
Spray it in your pen. Go back up to it so I can see the top.
Once my dad took one of those like latex disposable gloves and blew it up so it looked like a turkey
Oh,
balloon.
they will, yeah.
Here, if you two tie onto strings, then we'll use them for a minute to cool them.
Remember my experiment when I did the balloon thing?
So
For my
go to the
project
top and we'll check
last
through
week.
it.
I liked it. I thought it was
There's
good.
tons. Okay. How'd you get the 22,000?
I was scared because I put the game in my bag and like the marker was fading. I was like, oh god, no, no marker.
I'm gonna fail. This is
Whee!
That should be.
It was way more developed than my iPhone case one I did that one time.
yeah.
Where I had the like the Spider-Man phone and
Yeah. Did your phone break? Like this one?
Yeah.
They broke it in half and had the little clicky like.
Maybe that.
Yeah. Take a
Divide
picture.
it by-
Isn't that your brother's?
Yeah, and he
Oh,
knows.
no wonder it keeps on getting smaller. There's a hole in the back of it.
Oh.
That's why you.
It's like blowing up. I'm like, what's happening?
Hey, I can't believe you guys didn't even make it in the second round.
Square
It's because we didn't have any negatives. All the other ones were
Oh,
from
it's
Baltimore.
magic.
Yeah, because like Matt.
Oh,
was
it
with
should
me.
be the
Matt was with me last time.
it's not the thing.
He was like,
No, there's
I'm not doing
Is
it.
it
There's only two good
tens
bands.
and a
One
negative
was
6, not
one that guy
times?
is like just.
Oh, it's too heavy.
You're like raising to the exponent of negative 6 instead of those 10 to the negative 6.
Oh, kind of feels weird.
Oh god! See, I got a new balloon.
No, that was
Alright.
Do you
mine.
have another
So
balloon? Because mine
don't,
have.
don't raise it to
Mine
the
have a hole in the
exponent,
back of
like raise it to 10 to the exponent. Alright, we've worked it out, Sam. Okay, so put your balloons down and don't touch them while we do a little more
This is the
math.
dice. Do you have another?
Oh, yes.
Little hole in the back of it.
Aw.
This is my baby.
It's like everyone's like blowing theirs up fast, and that's blowing mine up. I'm like,
I'm sorry. The first year I taught this class, we started the class with 6 students, 7 balloons, and we almost didn't get to finish the experiment because they popped so many balloons. We had 1 balloon. I'm like, anyone pops this balloon and we're just done for. But I have the emergency PVC pipe just in case we do pop every balloon. But don't.
PVC?
Yeah, you can charge it.
Oh,
Which
okay.
also got a lot of laughs. But
Oh, hey, you know that thing that you have me throw away in the trash can?
yeah,
The wind blew, and it blew everywhere, all that stuff.
good thing it all reacted then.
It almost got, I was so scared it was gonna get on me.
It's pretty safe in its current state. It's
Oh, it was?
Just before, like when it was orange, it was not necessarily the safest substance known
You
to
said you could
mankind.
get cancer from it?
Yeah, hexavalent chromium is carcinogenic.
What stuff?
bad.
That just sounds bad.
But it's
It
trivalent.
has hex in it. Okay.
It just means that it, remember in module
This you're gonna
16
pop.
last year, you had like the,
We did it at the old building, behind, on that port,
Yeah.
like, near that stairs.
but like you
remember that?
have,
Was it the
Which
sulfur?
one?
no,
That
the
was
ammonium
sulfur.
dichromate.
smelled bad.
No, the one that was like, it
Yeah.
looked like a volcano.
That was
Yeah.
sulfur. The sulfur.
No, it was
like,
ammonium dichromate.
It
No
was?
sulfur, yeah.
Wasn't
that's
the
not
one that
sulfur.
Yeah,
I
it was.
did from?
She just said it was diammonium.
Yeah, but it had sulfur in it. That's
No,
why it's.
no sulfur in
It
it.
had no
Well,
sulfur.
I think
smell
I
bad.
did that for one of my
Because
lip
other
products.
Josh.
things and sulfur smell bad.
I can see everything in your pockets.
And I had to get like these big,
Oh.
thick rubber gloves because.
Oh yeah, you don't want to touch that stuff. It's
So
exciting.
that
Yeah.
there's like sugar and something else.
All right, so
Yeah.
listen. We have number 4 says, has that camera died yet or anything?
Not yet. It says
Okay.
low battery though.
Okay.
He's
Which
probably
sounds cool if I talk
crying
into the
right now
balloon.
seeing me.
I
It like
know.
echoes in my nose.
Like, we should just tell him to
Wait,
stop halfway through. Number 4 says 3 charges, none of which are forced to stay stationary, are arranged thusly. So you've got 2 negative charges.
you can see through the balloon.
One on each side of a positive charge. Explain why the instantaneous electrostatic force on the negative charge in the middle is 0. Well, why is that?
Because the ones on the outside are just exactly the same.
They're pulling with equal force.
Okay, equal and opposite force means no net force, right? So if you have, what are these guys? These guys are positive. Okay, so we've got a positive here, we've got a negative here, we've got a positive here. These distances are equal. So they are both attracting the positive equally so it doesn't move. Now, did you guys learn how to draw the no?
No.
Okay.
Didn't learn how to draw anything.
We'll talk about that in a minute then. Alright, number 5, 3 charges are arranged pretty similarly, except they're all positive. What is the instantaneous electrostatic force on the middle charge? So how will we find that out?
What number is it?
This is number 5.
Okay.
They're all positive.
Well, you'll just use the force equation
And like straight down.
again.
Josh, pay attention.
Oh, sorry.
Yeah, Josh.
Especially with the lab, you gotta do it and pay attention. So we have 1.5 meters and 2 meters. So we're gonna use that force equation. Alright, and we plug in our constant, our 2 charges, and our distance. And which distance are we gonna pick?
That one. 2.
So we're gonna have 2 forces here. So the first force will be, and we all know the fun units here, Newton meter squared per coulomb squared. Now, and the first force will use the charge of this and the charge of that. So we'll say 6.4 coulombs times 1.2 coulombs divided by the distance squared, which is 1.5 meters squared. So what's my first force gonna equal? The force between these two.
3.1 times 10 to the 4th newtons.
Yeah, that's what I got.
You did it. You lied to me.
Anyone else get that? Did I get that? Okay, and then I'll just make a note, which way is that force pushing on the middle particle? Is it pushing to the left or to the right?
Are we
To
talking
the
about the
right.
one on the left or the one on the right?
We're talking about this one applying the
Then
force on the.
pushing to the right.
It's pushing to the right because they're repelling each other. So I'll just make a note there of my vector. And then I'll find the other force between the other particle and the middle particle. And I'm not writing this unit here, times 6.4 coulombs times 9.1 coulombs divided by 2.0 meters, that quantity squared. And what do we get for that?
Just regular 1.3 times 10 to the 6.
Just regular is called positive.
And which direction is that force pushing the 6.4
Left.
coulomb particle? To left.
Whoa.
So what is the net force gonna be?
Oh, that is so cool.
Which one is
Stop
bigger?
distracting me.
Is the force pushing to the left or to the right, the larger number?
To the left.
To the left, so we know that it's gonna be going something to the left. So what is my magnitude of going to the left?
Negative 1.0 times 10 to the 5th.
Ooh, I stole somebody's calculator, that's definitely not mine. Tell me
Oh,
again.
that's it. Your exact same one, though, right?
Negative 1.0 times 10 to the 5th.
Newtons to the left, and that's what I get. Then B says if you were to make the 1.2 microcoulomb and the 9.1 microcoulomb charges stationary and remove the other one, what would the electric field be at that middle, well, at the point, not even the middle point, but like right here. So we're removing this guy, and now we're making these two completely stationary. What is my electric field right here? So what's the equation for that? Did you guys even read that far?
No.
Right. So you'll read that far this week, and
And the unit's not in newtons, right?
newtons per coulomb, I think.
Oh, then I did it wrong.
So does it make that third guy?
So newtons are coulombs. Maybe
Josh. Josh.
Sign doesn't know just magnitude. So when you use this equation that we're about to use, the sign, negative and positive doesn't matter, just the magnitude of the charge. So which charge are we going to use to figure that out? I'm gonna
They're
erase
dancing.
this. So did anyone make an attempt at this even though you didn't read that far?
Yeah, I got something in newtons, so
You
I
got
think
something
I
in
did it wrong.
newtons. Okay, so for B, we're going to use this equation. We're going to use E equals F over Q sub 0. So it wants us to find the electric field. So we calculated F to be this, 1.0 times 10 to the 5th newtons to the left, which we don't want to forget about. And we need to divide by Q sub 0. Well, what is Q sub 0? That's the big question. So it says here in the problem, if you were to make the 1.2 microcoulomb and 9.1 microcoulomb charges stationary and remove the 6.4 microcoulomb charge, what would the electric field at the point where the 6.4 microcoulomb charge had been be? So I don't understand how I did this problem for any reason, honest to goodness. I hope that camera dies soon. Give me a second.
Which problem is this?
This is 5B.
The
I
battery
really-
is alternating red and white flashing.
Go ahead and turn it off while we fumble around for a minute.
Goodbye, Sam. My hand